Okay, so I'd like to thank the organizers for inviting me to give the talk, and I'd also like to acknowledge my coworkers, Alvaro Islas and Anna Kalini. And so, so today we'll be talking about the routes to stability for spatially periodic breathers of the NLS equation. And so to start, deep water extreme waves may appear in a regular wave field due to the modulational instability of the background state and nonlinear focusing of uncorrelated waves in a localized region of the sea. One of the simplest models for studying phenomena related to the modulational instability is the nonlinear Schrodinger equation. Now, the NLS is a completely integrable equation, and it possesses a large family of special solutions which have come to be regarded as prototypes for rogue waves. For periodic boundary conditions, we have proposed in-phase NLS solutions, and you have the more tractable heteroclinic orbits of modulationally unstable solutions, such as the Stokes wave, which include the Akhmediev breathers. And these are the subject of our talk today. And so we're calling these Akhmediev breathers, we're calling them spatially periodic breathers, and I have the acronym SPBs. And so also for the infinite line, you have peregrine type rational solutions that decay polynomial to the ground state in space and time. So these heteroclinic orbits of unstable in-phase solutions have proven useful in modeling or providing insight in rogue waves over both uniform and non-uniform John Swap backgrounds. Okay, so the simplest unstable solution of the nonlinear Schrodinger is the Stokes wave, and in this case, it's well known that the Stokes wave is unstable to long wavelength perturbations with the following instability criteria. So if 0 is less than uj squared is less than 4a squared, then u naught has n unstable modes, where n is the largest integer such that n is less than al over pi. And so the important point is that each of these unstable modes has a heteroclinic orbit characterized by the wave number mu sub j, and we have the formula there. And so actually, for each j, there's a family of solutions parameterized by tau here in the one mode case. And if you have more than one unstable mode, for m greater than or equal to, you have these multi-mode SPBs, which are given, I'm just giving the form of this solution. And this is what we're calling in-mode SPBs. And so in the example, the plots at the top, we have A and L such that the Stokes wave supports 2 unstable modes. And then you have 3 possibilities of SPBs, for this Stokes wave. You have in the first plot, the first plot is showing the amplitude of the one mode SPB that's associated with the first unstable mode. And then in the second plot, you have the one mode SPB associated with the second unstable mode. And then finally, in the third plot, you have the 2 mode SPB where the modes are actually coalesced. And so perhaps that wasn't the best plot. It would have been maybe better to show where they weren't coalesced. But again, you have a family of solutions that are parameterized by rho and tau there. Okay, so recent studies by Seeger show that damping, even when very weak, can have a stronger effect on the modulational instability of deep water waves than was previously recognized. And so in this talk, we examine the effects of dissipation and higher order nonlinearities on the evolution of in-mode SPBs in the framework of the following damped equations. So we're looking at the linear damped NLS, and then you also acknowledge that a more accurate description of the wave dynamics is provided by the Disti equation. And so the Gramstedt-Trulson equation brings the Disti equation into Hamiltonian form. And so we are considering a damped Gramstedt-Trulson equation, and we're labeling this as a damped higher order NLS equation. And so we're going to consider initial data generated using the SPBs of the NLS equation. And again, the SPBs are over Stokes wave with in unstable modes for n going from 1 to 3. Okay, so the goal is to obtain a broad a broad categorization of the routes to stability of the SPBs and how to, how they are distinct, what are the distinguishing features of the damped flow. And so by this, I mean, which integrable instabilities are excited by the damped flow or the damped, not, higher order NLS. And how this depends on the mode structure of the SPBs as well as the instabilities of the underlying Stokes wave. So our approach is to view the damped dynamics as near integrable and to analyze the perturbed flow by appealing to the Floquet spectral theory of the NLS equation. And so an outline of the talk is then that will, I'll start by presenting just some elements of the NLS spectral theory. And we also have to have a broadened Floquet spectral characterization of instabilities. So the higher order NLS equation, to examine it, you see that it breaks the symmetry of the SPBs. And in the damped higher order NLS experiments, we find that instabilities arise that you can't capture by complex double points. Most of the evolutions, you see growth, but you don't see any complex double points appearing in the evolution. And so to address this, we present a, Floquet spectral characterization of instabilities for generic solutions. And so, after that, we then, look at the numerical experiments, for the damped NLS and higher order NLS equations. And finally, via perturbation analysis, we examine splitting of the complex double points present in the Floquet spectrum of the SPBs initially under the damped NLS and damped higher order NLS equation, which confirms that it confirms the short time spectral evolutions that we observe. And in some case, actually, longer time evolutions. Okay, so how can we characterize these linear instabilities? So the stability of a simple solution like the Stokes wave is easy to determine, but for more general solutions, we appeal to the spectral theory of the NLS. So your general periodic solutions of the NLS can be represented in terms of a set of nonlinear modes whose stability is determined by the Floquet spectrum of the spatial part of the Zakharov-Shabat system. And the Floquet spectrum of a solution U is given by all complex lambda such that the operator L has bounded non-trivial solutions. So if we let M be a fundamental solution matrix of the Zakharov-Shabat system and define the Floquet discriminant delta as follows, then the spectrum has the following representation in terms of delta, that it's all complex lambda, or all lambda in the complex plane such that delta is real and the discriminant is bounded between -2 and 2. And so the Floquet spectrum for a general in-phase solution consists of bands of continuous spectrum, including the real axis and the discrete set of periodic anti-periodic spectrum where delta is equal to ±2. And so I'm just going to call it periodic in the future. The endpoints of the band of spectrum are the simple points of the periodic spectrum, and they correspond to stable active degrees of freedom. And located within the bands of spectrum are two important spectral elements. You have your critical points of spectrum determined by the condition that d delta d lambda is 0. And you have double points of the periodic spectrum. And so these double points are critical points, but they are also elements of the discrete spectrum where delta is equal to ±2. And we're limiting the degeneracy here, at d squared delta d lambda squared is not 0. So there's an important distinction between the real and complex double points. The real double points correspond to stable inactive modes, and the complex double points are related to linear instabilities of the periodic solutions. And this was recognized a long time ago by Ercolani, Forrest, and McLaughlin in the 80s. And so people have always recognized the significance of complex critical points, but I don't think that they were examined that much in the perspective of having instabilities. So in this case, we find that instabilities are associated with degenerate complex elements of both the discrete and continuous spectrum. And so again, even though the double points are critical points, we're going to call them complex double points and complex critical points just to be able to distinguish the two. Okay. So the Floquet spectrum for the Stokes wave, going back to our simple example, the Floquet discriminant for a Stokes wave is given as follows. And so the spectrum consists of the entire real line and one band of spectrum ending, the band of spectrum ends at plus or minus IA. And so there are infinitely many double points, but the number of imaginary double points equals the number, the number of imaginary double points is finite. It satisfies the 0 less than j less than al over pi, and it equals the number of unstable modes of the Stokes wave. So at each complex lambda sub j, we can construct for each one of these complex double points, we can construct a heteroclinic orbit using a Becklin transformation, and an M-mode SPB is obtained by M iterations of the Becklin transformation. So finally, an important property of the Becklin transformation is that it's isospectral. And so in the numerical experiments, just as heads up, in the numerical experiments, we were considering XBBs over the Stokes wave with 1 to 3 complex double points. So initially, their spectral configuration is going to look like the figure here at the, in the plot of the spectrum. That top plot is the spectrum of the plane wave. So initially, it's going to look like that, and I'll be showing the spectrum at later times. But this is its initial state with either 1, 2, or 3 complex double points in the upper half plane. And so due to the symmetry and the spectrum, I'll just be showing the spectrum in the upper half plane in the various plots. Okay, so previously we examined analytically and numerically, and so this is, just to step back a little bit to address the issues that Piotr was raising last week. That we had examined analytically and numerically the linear stability of the SPBs with respect to a variety of random perturbations of initial data. And so the key observation used was that for a given solution of the NLS, its squared eigenfunctions satisfy the linearized equation about U. And so using the Becklin gauge transformation, we can obtain the new potential, the SPB, as well as its eigenfunctions. And so the eigenfunctions of the M-mode SPB when M is less than N, so you're looking at a non-maximal SPB. And as an example, this would be U1 in the 2 unstable mode regime. When you evaluate the eigenfunction at the second double point, nu2 here, then the eigenfunction is given as follows, and the functions B are bounded functions of x and t, and you have, of course, this exponential growth factor in front. So the associated squared eigenfunction solutions of the linearized NLS at U1 grow exponentially in time, and U1 is unstable. However, the eigenfunctions for a maximal SPB when M equals N, for example, U1 in the 1 unstable mode regime, or U2 in the 2 unstable, U12 in the unstable mode regime. The eigenfunctions for U1 here are given there, and I'm only writing down the component, the first component, but you can see that the eigenfunction is bounded. This component is bounded, and the first component, that was the second component. I'm sorry, that was the second component. The first component is also of a comparable form and is bounded. So there's no exponential growth in time. And so we refer to this as a neutral or orbital type stability because of the fact that there was no exponential growth, that the instability of the plane wave had been saturated by this Becklin transformation. And so this can be seen to a certain extent in the plots we have here. So this is the numerical portion of that analysis. And so, so to numerically examine stability, we had 6 different types of random perturbations with random phase, random noise, random amplitude, random Gaussian, high frequency, low frequency types of perturbations. And so what we are showing here in the first row is a series of contour plots, and you are superimposing the perturbed solution U delta on U for the 3 different cases. And by U, I should clarify that this is a member of the family, a closest member of the family to U delta. And so, so that's the first row. And then in the second row, you have the averages of the H1 norm difference between U delta and the closest member of the family over all experiments in that particular perturbation ensemble. And again, where I have this row star, that's indicating that you're looking at the closest member of the family to U delta. So from the contour plots, you see that U delta and this closest member, in the case of the U1, the first column is U1 in the 1 unstable mode regime. And in the third column, it's U12, the 2 unstable mode, SPB in the 2 unstable mode regime. You can see that the contour plots are visually indistinguishable. And if you look at the corresponding growth in this difference, you see that for U1 and the 1 unstable mode regime, in the worst case scenario, the 10 to the minus 4 perturbation has grown to 10 to the minus 3. And in the case of the U12 in the third column, you see that it has grown to order 10 to the minus 2. And this was for a uncoalesced SPB, but if you looked at actually the coalesced SPB, then the error actually is 10 to the minus 3. And so these perturbed solutions remain close to a particular member of the respective family for a significant period of time, which is indicating an orbital type of stability. So there's this stability in the waveform. And so in the middle column, which is the case of the non-maximal SPB, you see that the contour plots are quite different, and also the difference in the solutions grows to 18 or 10 there, 10, 18. So it's unstable, which nobody has questions about. But I think, in one possible resolution is that, in light of Piotr's very interesting discovery of this extra generalized eigenfunction, one possible conjecture is that it's related to some sort of phase instability, exponential growth in the phases. And so, okay, so, going back to our, issue of, so we have established that initially these SPBs are when they're non-maximal, unstable, and then there's this open question of how you want to classify the stability when it's a maximal SPB. Okay, so we're going back to looking at what happens to them once, once you have damping. But as I said, to address the higher order NLS dynamics, there were cases that showed growth, but there were never any complex double points in the spectral evolution. So we needed to examine what other elements of the spectrum could be a signature of the instabilities, these instabilities. And so, the clue was provided by looking at this even three-phase solution of the NLS. And so, that's its spectrum, the amplitude is presented there along with its spectrum. And you see that you have two bands of continuous spectrum in the upper half plane. And since the discriminant, the derivative of the discriminant with respect to lambda is 0 at transverse intersections of bands of continuous spectrum, lambda c is a critical point where they intersect there. So there's no complex double points, but there's this complex critical point in the spectrum. So if you take small symmetric perturbations of the initial data, then you will produce a spectrum that is topologically equivalent, and the waveforms will be delta close. However, for asymmetric perturbations of the initial data, topologically different spectral configuration is obtained. The critical point lambda c has split into lambda c plus minus. And that's, you can see, this is the, in the plots you have the amplitude of the waveform showing this, this modulated, traveling, waveform traveling to the right. And in the second plot, you have the spectrum for this perturbed solution. And so if you look at the difference between the perturbed solution and the original even solution, you see that the difference grows to order 1 for these asymmetric perturbations. And so we associate the transverse complex critical points with instabilities arising from symmetry breaking, which are not excited when evenness is imposed. And so the exact nature of this instability is still under investigation. And so I should have mentioned that back when I was looking at the plots of the contour plots for the SPBs, that you do see with these perturbations that there's this slight growth of asymmetry in the problem, that the error or the difference is coming, it was a random asymmetric perturbation to these waveforms. And so you see that there is this asymmetric growth of asymmetry in the problem. Okay, so going back, then, so the last issue is that, in the damped higher order NLS experiments that we'll present, they corroborate the significance of these critical points of the continuous spectrum in identifying stabilities in the unrestricted solution space. Okay, so let's look at our numerical experiments now. And so so to complement the Floquet spectral analysis of the data, we investigate the excitation of instabilities in the damped flow by monitoring the growth of small perturbations in the following form. So you're basically perturbing in a direction in one of the other directions. And so we monitor the evolution of the H1 norm of the difference. So that's our D of T. So instabilities are being excited by the damping and higher order nonlinearities. And so loosely speaking, we say that these instabilities have been saturated when D of T stops growing. Okay, so we're looking at the one mode SPB U1 in the one unstable mode regime. So this would have been a this would have been the maximal SPB, and you know, would be classified as a maximal SPB in this case. And so in the plots, you have the surface of U1 and of the damped SPB, and then you have, you know, three significant spectral plots. But let me show you a movie, if I can manage to do it. Let me show you a movie where you can just see the evolution of the spectrum rather than just, in this case, it's actually nice. The movie is very clear. Once you have a lot of or several, even with two instabilities, then the evolution, you know, you have to stop it frame by frame to look at what's going on. But here it's very obvious what's going on. Okay, so this is, again, initially you have one complex double point which is being indicated by the X, and so you see it open up into a cross state. And so as it evolves, the cross just widens, the bands of spectrum widen until eventually that vertex of the cross hits the origin, and then the bands move off. Okay, so that was the movie of the spectrum, the evolution of the spectrum. And what you see is that complex double points never form in the spectrum. Also, complex critical points don't form. And the evolution of D of T confirms that there were no instabilities excited. And so the damped SPB can be characterized as a continuous deformation of the characteristics of or an even NLS three-phase solution. And so the amplitude of the oscillations decrease and the frequency increases until small fast oscillations about the damped Stokes wave are present. Okay, so what happens in the higher order NLS? So, you know, I'll be toggling back and forth between, you know, some of the experiments for NLS and then the comparable ones for higher order NLS. And I'm not going to present all of them, it's just a few. So, okay, so for the higher order NLS, you can see the wave, the amplitude of the waveform there in the first plot. But here, let me show you the movie for the evolution. So you see that it asymmetrically splits, but it period or intermittently comes back into an even state where you have a critical point in the spectrum. And so, the first time this occurs is at t equals about 10, which is why that state was shown. So you see the asymmetric splitting in the first plot on the spectrum, and then you see the cross state, the even state forming, which then has this instability associated with it, and it splits again. And so it does this splitting intermittently until about t equals 28. And if you look at the evolution of D of T, you can see that you have these weak instabilities. I mean, they're of course being damped simultaneously, but you do have these instabilities being excited and then quelched by the damping until about t equals 28. And so this is confirming, in this simpler case, that already it's confirming the significance of these instabilities associated with the complex critical points. Again, you know, acknowledging that they're probably weaker instabilities than for complex double points. Okay, so moving on to the two unstable mode regime. Yes?
Constance, sorry to interrupt you. Maybe it will be time to conclude because we're running a little bit.
Okay.
Sorry for this.
That's okay, that's halfway. Okay, so let me jump to the conclusions here. And so let's jump to the conclusions. And so in the conclusions, we have that these novel instabilities emerge in the damped higher order NLS that are not captured by complex double points. And so by examining the stability of an even three-phase solution with respect to non-even perturbations, we find that instability is associated with these transverse complex critical points in its spectrum. And so this association of instabilities excited by symmetry breaking was complemented or corroborated by the numerical experiments. And so if you don't have damping in the problem, which, you know, I didn't have prepared for here, you know, the growth is much more significant than what you're seeing in these damped experiments. And so So, you know, growth from all the instabilities that are being excited saturates once, you know, damping, you know, eliminates all the complex double and critical points in the spectral decomposition of the NLS and higher order NLS data. And so the thing I didn't get to show is that if you looked at U2 in the two unstable mode regime, then you see that only certain modes resonate with the damped NLS and higher order NLS perturbation. So resonant modes aid in stabilizing the solution, and if non-resonant modes are present, their instabilities persist and organize the dynamics in a longer time scale. And so, you know, again, acknowledging that these instabilities with the complex critical points may be weaker, but again, it's something that's still under investigation. And once you get to a couple of more unstable modes, the impact, you know, can be significant from the complex critical points. Okay, and so we also had a short time perturbation analysis for both the damped NLS and higher order NLS flows, where we found that the resonant complex double points split while the non-resonant complex double points remain closed, corroborating the short time spectral evolutions observed in the numerical experiments. And so this was done by mapping the damped NLS, for example, mapping the damped NLS equation to you know, a variable coefficient NLS equation, and then, you know, looking at that solution for, you know, getting an approximate solution to that for a very short time, and then linearizing that approximate solution to get the you know, data for the perturbation analysis to start with on the perturbation analysis. Okay, so I guess that's it. And if people have questions, or I could show maybe some more during in a chat room or break room or whatever. Okay, so I guess my time is up.
Thank you very much, Constance. We won't have time for question right now. So what we'll do, we will go for this, no? Oh yeah, there is a break actually. So we are coming back at 4 p.m. for the plenary talk.